coming to the operation amplifier symbol and terminals, this is the pin diagram. This is how it look like. You can see embedded into it. 741. Every integrated circuit will have its pin number inscribed into it. Definitely. Otherwise, we will not be able to distribute because there are many ICs which have 8 pins. Unless and until I know what is the specific pin, I mean IC, I will not be able to decide what can be the IC put to application. Hence, every IC, even you can check in your motherboard, whatever, wherever you get hold of an IC, definitely pin number will be there. Also, some letters like this indicating will be there. This letters indicate the manufacturer. Every manufacturing company will have its own code. For example, mu A, Cn like this. So you'll have that also inscribed into it. And coming to the 741 IC, the commonly package is the 8-pin package. So this is the pin diagram of the IC where you have 8 pins. Of these 8 pins, 5 are the workable pins. Remaining 3 pins, that is this offset null 1 and 5, and the pin number 8, no connection or not connected, is not at all used. This 1 and 5 offset null is used for one specific purpose. When I'm doing the characteristics of this op amp, I'll tell you how this is used. 8 is never used. Probably for any interconnection I can use, but otherwise it's not needed at all. The actual pins that is used is two inputs, one inverting input pin number 2, one non-inverting input pin number 3, and one output pin number 6. And to power up the IC, I need two supply voltage sources, one positive supply and one negative supply. So that will be pin number 7 for positive power supply, pin number 4 here for negative power supply. So that is what is given over here. This is the functional diagram, that is your symbol representation of op amp, and this is the IC structure of your op amp. So whatever I've told you is given here. And coming to this pin input pins, I told you one is inverting, one is non-inverting. We've already discussed this. Whenever I give input via the inverting terminal, output will be always phase shifted by an angle of 180 degree, or I'll get a negative polarity, depending on whether it's AC or DC. If I give the input via the positive terminal, that is your third pin, this pin, the output will be same phase angle as that of the input. That is what is given here, pin number 2 and 3. Okay, this also we've already seen. This is the internal block diagram of the operation amplifier. IC741 is exclusively called operational amplifier because using this IC, all your basic operation, that is mathematical arithmetic, addition, subtraction, division, multiplication, and logical operation, all your gates, basic gates, and or not everything. Apart from this, some other additional application also can be performed using this. So since all the basic mathematical, arithmetic, and logical operations can be performed, we call this as an operational amplifier, or in short, op amp, right? So this is the internal block diagram of op amp. Basically, I'll have many number of transistors interconnected into it into a single chip of silicon. So let's see how the transistors are connected. So I have two stages of differential amplifier. One differential amplifier needs two transistors. So this itself will make for two sets of transistor. This is an isolation amplifier or voltage follower. This is acting like simply a buffer. That is, the output of the second stage should be connected to the input of this power amplifier. What will happen is the impedance at this point of the output may not be same as the impedance at the point of input. So I need some device in between which will match both the input, but still there will be no amplification. That is why it is a voltage follower or a simply buffer amplifier. So this will connect these two stages together so that this output impedance and this input impedance matches with each other. And the fourth stage is the power amplifier. We've already seen the power amplifier. Out of all the power amplifiers, class B push pull amplifier is the best type of one because it offers me output in both the half cycle, plus it provides with good efficiency. So that is, or it can be a Darlington pair. This is beyond your syllabus, so I'm not going into detail of Darlington pair. That is also a amplifier which will give me good amplification. That's it. So we have four stages. Ultimately, the output comes out of the power amplifier. So this entire blocks are all together embedded into this IC741. Okay, this we have already told you. inverting and non-inverting. So when I give the input to the non-inverting, as you can see, the positive and negative half cycle, there is no phase shift in the input and output. But inverting, during positive input, I get negative output and vice versa. So depending on which input, where you give the input, the output will be either 0 degree with respect to input or phase shifted with respect to input. Okay. Next, moving on to ideal operational amplifier. Basically, first we'll have to see uh, uh, what we are going to see now is characteristics of amplifier. When I say characteristics of amplifier, I'm going to define how the amplifier can behave with respect to the input, output, input impedance, what should be the input impedance, what should be the output impedance, what should be the workable bandwidth, etc. And in this, we have two cases. One is called ideal characteristics, the other one is called practical or the operational characteristics. So to determine the ideal characteristics, I have something called ideal operational amplifier. So this is the symbol of op amp. I have two inputs. This positive and negative power supply need not be shown all the time. It is understood by default. It is present. When you're drawing op amp, it will be simply a triangle like this with two inputs and one output. It is not necessary always you should mark this pin number 7 and that is positive and negative power supply. That is not mandatory. Okay. Okay, this is the normal op amp, and this is called the equivalent circuit of op amp. What I've shown here is, see, I have two inputs V1 and V2, and this Ra is taken as the input resistance. At any point of input or output, I will have some internal resistance. That is what I've taken as Ri. Then what happens here is, I told, we've already seen in the previous slide, we have lots of amplifiers embedded as the internal components of op amp. So which means internally I have a source, voltage source there inside the op amp. That is what is represented as AOL into VD. This symbol indicates it's a dependent source. That is, VD is the source. It is dependent on open loop gain of the amplifier. So this source is named as AOL into VD. So every time this gain changes, this source value also will change. And this gain depends on what is the input I give at this point. So I have this internal voltage source, which is a dependent source. And finally, I have the output resistance. Any output will have its own resistor value. That is what is termed as output resistance. So ultimately, when I measure what is the voltage drop here, it will be same as this drop. That is why V naught is given as AOL into VD. So in short, if I want to represent an op amp as an equivalent circuit, I will be representing like this. Two sources, one input resistance, one dependent source inside, one output resistance, and net output voltage. As you can see, input resistance is connected in series, I mean this way, between V1 and V2, output resistance only at the point of output. So this is your equivalent circuit of op amp. Now, for as I told you, the reason we are going for this is I'm going to classify the characteristics of op amp as ideal characteristics and operational or practical characteristics. Now, coming to ideal characteristics of op amp, open loop gain. Open loop gain is nothing but AOL, which we saw here. This AOL is called open loop gain. This open loop gain is always taken as infinity. First point. Second, input resistance is taken as infinity. Third, output resistance is 0. Bandwidth is infinity and offset voltage is 0. Now I'll explain one by one. First one, open loop gain is infinity. That's because now see here, my see in this expression, if I rearrange this, I'll be getting V naught by VD is equal to AOL. So can I say V naught is the net output, VD is the input at this point. So can I say AOL is the net gain of the amplifier now? So if I take AOL as the net gain of the amplifier at this point, look at this. Generally, any electronic circuit, the ideal condition is getting highest possible gain. So what is the highest possible gain available? Only infinity. So ideally speaking, the open loop gain is always taken as infinity. Am I clear with this? Do you want me to repeat this part? Anybody?
No, ma'am.
Right. Next one is input resistance is infinity. Okay, coming back here, this is my input resistance. See, whenever resistance is high, it will draw very less current. So, assume this resistance is infinity. So, what will be the current drawn by this? It's going to be practically zero, which means even though it draws input less or zero input current, it is going to give me a very high or maximum output. So, ideally speaking, this resistance is taken as very, very small, or I mean very very high or infinity, so that because what I want is whatever voltage I give at the point of input should be fully transferred at the point of output. Now imagine if I have a drop too much of drop over at this point, that voltage which I give here will not fully get transferred at this point. So, which means the current drawn through this resistor should be very, very small. Only then this drop also will be very small. So, whatever voltage I give here fully will come at the point of output. So, for the current drawn here across the input resistor to be small, or definitely the input resistance will be very, very high. Ideally speaking, when I say high resistance, it is only infinity. So for that purpose, input resistance or input impedance should be always high or infinity as an ideal characteristic of op-amp. Got it? Okay. Third one is output resistance is zero. This is also for the same reason. Now listen, this is my output resistance. Now, if I have output resistance as very high value here, I mean, if it is zero here, what will be the current? For less resistance, always current is very high. Now, whatever is the voltage here, that is what is up. When I take it as a closed loop, this voltage will be summation of these two. So, which means the entire drop will get added to this. Now, imagine if this resistance is very, very high. So what will happen is the current drawn by this is going to be very, very small, which will not provide me a good output at the, I mean, good voltage at the point of output. Hence, output impedance should be very small. When I say very small, smallest number available is only zero. So ideally speaking, output resistance is taken as zero. Okay, next comes the bandwidth. We were discussing this bandwidth even in the oscillator. Bandwidth is nothing but usable range of frequencies. When I'm doing UJT relaxation oscillator, I'll draw a frequency response and explain what is this bandwidth clearly. For now, you understand. See, now this is my op amp. Operational amplifier can be worked with AC input signal as well as DC input signal. Okay, coming